Okay, hello everyone. My name is Aryan. I am 13 years old and I am studying in 8th grade. I was born in Bihar but I am living in Ludhiana for my education purpose. And for today, our topic would be about special and general relativity. Introduction to relativity. Einstein theories revolutionized our understanding of space, time, and gravity. They describe how objects behave at high speeds and in strong gravitational fields. These theories have been confirmed through numerous experiments and observations. Some historical background. So it was first proposed by Albert Einstein in 1905 and general relativity followed in 1915 as an extension to include gravity. Prior to Einstein, Newton laws dominated the understanding of physics. So the special and special relativity, it means like special cases where the gravity and acceleration are not included, and in general relativity, it is more generalized. It includes the gravity, acceleration, the bending of space-time, and many other things. So why we need special relativity? So special relativity is resolved the conflict between Newtonian mechanics and Maxwell's electromagnetism. Newton suggested speeds are relative, but Maxwell showed light speed is constant. When the Michelson-Morley experiment failed to find a space ether, Einstein realized time and space must be flexible to keep the speed of light an absolute. So there were people uh, back in the day. Michelson-Morley, he was a scientist. He was trying to find a space ether. People in that time believed that light traveled in the vacuum of space, but that space was filled with the space ether, and but they could not what you can say detect it. And some of the physicists suggested time dilation and length contraction. They said that the earth is getting length contracted at a perfect rate and it's getting time dilated at a perfect rate, so that we could not even discover it, but it was later shut down because we couldn't just discover these things. The postulates of special relativity. The laws of physics are the same in all inertial frames of reference. The speed of light in a vacuum is constant for all observers, regardless of motion. These postulates lead to non-intuitive effects like time dilation and length contraction. So these two things, time dilation and length contraction, could be understood by the Minkowski's space-time diagram and the space-time interval equations. So the speed of light is in vacuum is constant for all observers regardless of motion. So so an example of time dilation and length contraction can be like, let's say that there's a spaceship going from uh, Earth to a star, and there's an observer moving at a high speed. So what would he see? That it has covered three it took 3.5 years to reach that. So these are the effects of time dilation and length contraction. So time dilation. So moving clocks run slower compared to stationary ones, has observed from an inertial frame. So this effect has been experimentally confirmed with atomic clocks on aircrafts. So time dilation is significant at speeds close uh, close to the speed of light. So it happens at relativistic speeds, and that and one way to think that is that everything in the universe is moving at the speed of light. So that is why uh, one thing cannot move at the speed of light in time, because it is always moving through space, and one person cannot move in space at the speed of light, because then it wouldn't run in the time coordinate. So that is why we cannot get reach the speed of light, and it can be one of the way to understand time dilation. As a speed increases through space, the time coordinate be uh, must be perfect to so that if we add them, it will result to the speed of light. So length contraction, and objects moving at relativistic speeds appear shorter along the direction of motion. This contraction only becomes noticeable at speeds approaching the speed of light. It results from the Lorentz transformation that relate space and time coordinate. Okay, so okay, I think so. Saksham has raised an has a question. So what's the question, Saksham? Yes, I have a question. What is Lorentz transformation? Okay, so Lorentz transformation. So we can say that these two things, length contraction and time dilation, are a part of Lorentz transformation that are used to make diagrams of an object, like the Minkowski's space-time diagram, to see how it's moving in space and time. Okay, so Saksham, did you understand these topics? Okay, so I have a question for you. Let's say that there's a spaceship moving at 80% the speed of light, and there is some light. So what would be the relativistic rel- relativistic speed of that light compared to the ship, to the rocket? Do you know that? So I'm saying, let's assume that there is a spaceship moving at 80% speed of the light, and there's some light alongside it. So how can we find the relativistic speed between the light and the spaceship? So do you know? O- Okay. So many people, what will they do is that, let's say that the speed of light is 100 units, and the speed and that of the units of that spaceship would be 80 units. So what we'll do, we will just subtract 100 by 80, which would be 20 units. But what does the laws of relativity say? That the speed of light is always in constant. So if we factor in the length contraction and the time dilation, what would happen, uh, that the spaceship would shrink in size, and its its clock would be moving slower. So then that would add up, and if we then find, it would the relativistic speed between them would be the speed of light. So did you get it? What did I say, Saksham? So like length contraction and time dilation happens, like as I said, when the spaceship was moving relative to the speed of the light, it would perceive the light traveling at c, not 20% the speed of light, because of length contraction and time dilation occurring. So did you get it? Okay. So ladies and gentlemen, any further questions? Satyajit, do you have any questions? Yes. So what happens that when objects move at very high speeds, they appear shorter along the direction of motion. So like as I mentioned, with the case of the spaceship, what would happen that it would shrink in size, and the time dilation would happen. It means that their clocks, like their 1 second in our clock wouldn't be the same for them, it would be a higher. So these all things happen to make up for that, so to conserve the laws of relativity, you can say. Yes. Okay. The Lorentz transformation. So these equations connect space and time coordinates between different inertial frames. They replace the classical Galilean transformation at high velocities, and Lorentz transformation predict phenomena like time dilation and length contraction. So these equations connect space and time coordinates and combine it into one called the space time. So if we take a diagram of an object accelerating at an uniform motion, what would happen that we would see, like if we make a graph of that, what would happen that we'll see that the hypotenuse of that a specific object moving at an accelerated uniform motion would always remain an invariant. But in space time, if we observe, what would happen that the perpendicular would always be an invariant. So these help us in finding these and drawing the Minkowski space-time diagrams, which help us understand how an object moves through space and time. So most and these are there are many geometrical properties, and there is also the endless horizon, which we'll talk about later in the presentation. So mass energy equivalence. So Einstein's most famous equation is E is equals to mc squared. It shows mass can be converted into energy and vice versa. This principle underpins nuclear reactions and particle physics. So there is one more thing called the relativistic mass. So that's why moving objects like kicking a ball moving at high speed and deflecting is more harder than kicking an ball at rest. So the concept of space and time. So space and time are interconnected into a four-dimensional continuum. Events are described by four coordinates: three for space and one for time. The fabric of space-time can be curved by mass and energy. So I have a question. So why does space curve? Does anyone know how it can be curved by energy and mass? Saksham, do you have an answer for that? Okay, so Saksham, I was saying that it's written here that mass can that the fabric of space-time can be curved by mass and energy. So do you know why is that? Why does that curving happen? Okay, so Satyajit, do you have an answer for that? Okay, okay, so like, uh, okay, so okay, so uh, let me just tell you something. If we take like there's some space on the earth and it's moving upward, and that too parallel. But what would happen if we apply it to an asteroid moving near moving near the earth, what would happen? It should be stretched. The Newtonian physics can answer that. But what about the Einstein's principles? So what happens is that, like, it's the reason for why the planets are round too. uh, let's assume that there's a graph, and if there are 2 points, we'll take 2 points on the planet, one at the end and one at the other end. What would happen? That they would have a world line that would go up, and they would be parallel. But if that's the case, it should be expanding. And Einstein took about half a decade to solve this mystery, and asked what could happen that this possible things can be happening. So he, like, on curved surfaces, what if we want to go parallel to each other, uh, we may we may need to increase the distance or shrink. Like on a globe, if we go parallel to each other, walk at a distance, we will meet at one point. And a straight line on a curved surface is called a geodesy. So he said that space and time are curved by mass, and that explained the stretching of these things. So that is one of the reasons why the planets are round. They tend to go in a spherical shape because they converge, and the mass beneath them resists. So that is why planets also go into an spherical manner. So, Saksham and Satyajit, did you understand it? Okay, okay, I think so. Saksham didn't. So, when we want to travel, let's assume that there are two people and they want to travel straight, like they want to travel parallelly to each other, and but that was not the case. They would meet at some point, and if they want to be what you can tell what you can call that, uh, if they want to maintain the proper distance between them, they have to travel inward, they have to converge or diverge, uh, and these are called geodesies. So the world lines, like, we'll assume the two worlds line at the planet's end, they converge each other, and the mass beneath them resists, and that is why the planets are round. So I think so we should continue with the topic. Introduction to general relativity. So general relativity extends special relativity to include gravity. It describes gravity as the curvature of space and time caused by mass and energy. Massive objects cause space-time to bend, affecting the motion of objects and light. General relativity. So general relativity purpose relays, it offers it offers a low cost for standard switching tasks in common appliances. It has special purposes which relay provide and optimize performance. So one very good use is of the GPS signals that we get. Those are related on the principles of general relativity. And one more thing we'll talk about is that everything moves at the speed of light, and, like, the speed of light isn't constant. So if we take any object, its constant speed is the speed of light, and because it's moving through space and time, and then their sum would be equal to the speed of light. So if we are moving faster in time, what would happen, like, if we are traveling faster in space, what would happen, that the time coordinate must be cut down uh, to maintain that speed of light. So the equivalence principle states that gravity and acceleration are locally indistinguishable. An observer in a windowless room cannot tell if they are pulled by gravity or accelerated through space. This insight allowed Einstein to generalize special relativity into general relativity, reimagining gravity has curved space-time rather than a force. So, I have a question for everyone. Why is the equivalence principle locally true? So, Saksham and Satyajit, do you have an answer for that? Hello, Saksham and Satyajit. Okay, so you are right. It must happen when the gravity is uniform, so not unequal. So that's one of the main reason it's local, the equivalence principle. Gravitational time dilation. So gravitational time dilation means time moves slower where gravity is stronger. According to equivalence principles, being deep in a gravity well is like constant acceleration. Since acceleration affects time in special relativity, generalizing to general relativity reveals that clock on Earth ticks slower than those in space. So these are so like the clocks on Earth and the ones in that are accelerating, they would be measured to be slower. So this is a gravitational time dilation and the Einstein's field equation. So these equation relate the distribution of mass and energy to the curvature of space-time. They are highly complex but form the core of general relativity. Solutions to these describe phenomena like black holes and expanding universes. So, I have a question for everyone. Can we outrun light? So, Saksham and Satyajit, do you have an answer for that? Uh, my question is, can we ever outrun light? Outract? Outrack? I didn't get your question. Yes. Okay. So my question. So I think he's asking about the question. So I was asking that can we ever outrun light? So that was my question. So did you get my question, Saksham? So what do you think? Okay, so but what would happen if we are on a spaceship that is accelerating at an uniform motion? So do you think can we outrun that then? Okay, so Satyajit, what are your views on this? Okay, so I wasn't talking about like we reaching the speed of light. I was talking about can we outrun the speed of light? Can we outrun light? So uh, I talked about this. What what did you say? Okay. So we will be talking about this topic. It's called the Rindler's horizon. So like it wouldn't have to touch messy equations, and we will just understand it by geometry. So it involves the hyperbolas, asymptotes. So we are going to talk about that, and it's a very interesting answer. Okay, so we, okay, so so I was talking about a spaceship that is accelerating at an uniform motion, and so okay, so uh, I think so we should talk about this later in the presentation, because I have an diagram for that. So we'll discuss it better with the diagram. Okay. Gravity has geometry. Unlike Newtonian gravity, which is a force, Einstein described gravity as geometry. Objects follow geodesics, or the straightest possible paths in curved spacetime. This explains why planets orbit stars and light bends around massive objects. Experimental evidence for general relativity. The shift of Mercury's orbit confirms predictions. The gravitational lensing observed when light bends around massive objects, the detection of gravitational waves from merging black holes, supports the theory. Black holes. So, black holes are regions of space-time with gravity so strong that nothing can escape it. So, they form from the collapse of massive stars. Black holes demonstrate extreme curvature of space-time. Okay. So, Saksham, I have a question for you. So, my question is, has we reached the event horizon, the time starts to slow down and it eventually stops. So, how does an event horizon then form anyways? So, like when something goes near a event horizon, what happens? It gets slows down, and when it reaches the event horizon, the time stops for him. So, how does a black hole even form at that point? Like the in the event horizon, what happens? The time stops. So how is that black hole even forming? Wouldn't it take infinite time? Yes. Okay, so do you know about relativity of simultaneity, that concept? Hello. Okay. Saksham, I was asking that do you know the concept relativity of simultaneity? Okay. Okay, so this has to do something with the relativity of simultaneity, and we'll discuss it later in the presentation. So I was just asking so that I was just checking, do you know these concepts? Okay, moving further. So gravitational waves. So ripples in space-time caused by accelerating of massive objects, first detected by LIGO in 2015, confirmed a key prediction of Einstein's general relativity, cosmology and the universe. The general relativity underpins our understanding of the universe expansion. The Big Bang theory is supported by the metric expansion described by Einstein. So, dark matter and dark energy are phenomena explained with this framework. Why does gravity bend light? So, gravity bending light isn't about a force pulling on photons. Instead, it's an inertial effect because an observer on Earth is constantly accelerating up, light appears to curve down. This insight helps solve the mystery of why gravitational and inertial mass are identical. So it's one of the main reasons why gravity, like if an object is 10 times heavier and it falls, what would happen that they will fall at the same speed because the gravitational and inertial mass get cancelled they get cancelled. So that is why gravity accelerates everything at the same pace. So okay, now we are going to the uh, interesting part. Can we outrun light? So no, we cannot outrun light. Relativity dictates that you must always travel slower than light. However, by constantly accelerating, we can create a endless horizon. This effectively leaves behind a patch of spacetime where light rays can never catch up to you, mimicking a black hole's event horizon. So, as you can see in the picture, uh, there's the point X and there's the future light cone and the past light cone. So we choose measurements like light years and light speed so that we can get a curve of 45 and 45. So, and what's so special about this? So it is the future light cone of light itself. So like we cannot like run at the boundaries of it. We can only uh, like we can, if we are always constantly accelerating at a uniform rate, what would happen that we will create an asymptote which will touch it when it reaches infinity. So okay, let's get to the endless horizon. So gravity bending light isn't about wait, I think so. Okay, so it let me get to the back. So as we see in that picture, if we in the green part, and the red part is the future light cone and the green part is the other space time, and if we focus on that, we can take in any point, and these all of them are hyperbolas to the middle. And if there's an accelerating spaceship, what would happen that it would be an hyperbola to that vertex that you see in the middle. And if that flashlight is behind one or two steps, like what would happen that it can touch it, and that ray of light would be called an asymptote to that hyperbola. So it means that flash of light would be touching that spaceship uh, after infinite time. But what would happen if that flashlight was before that particular point? What would happen that it would never reach up to it. So uh, did everyone get it? Saksham and Satyajit? Relentless horizon. Okay, so if we are accelerating, what would happen that we will leave a patch of space that we cannot access, and like the information from that zone won't be reaching us because we are traveling and accelerating at an uniform motion. So uh, it gives like a relation between that gravity. and acceleration can be interchangeable, and if there's a endless horizon and if that's in an empty space, that would be indistinguishable from an event horizon. So that's the endless horizon. And so did you get the part where I said that we can outrun light? uh, okay, so let's assume that our spaceship is here, uh, that green part, and it's accelerating at an uniform motion, so it would be an hyperpolar to this point. And if and if this flashlight of this is just one step behind, it would reach it, and it would be called an asymptote of that specific hyperbola, which will touch it after an infinite amount of time. So like that would be called the threshold, where if we put the flashlight, it can touch us, but after infinite time. But what would happen if that is behind us? If that the flashlight is behind that specific point, what would happen? That it would never be able to reach us. I know it sounds tricky, but it's about geometry and these things. So Saksham and Satyajit, did you get it? Okay. So relativity of simultaneity. So this is a concept we must understand to answer the questions of how are black holes forming. So relativity of simultaneity means that now is subjective and depends on a observer's motion, because world lines tilt due to relative speed. Observers disagree on the timings of distant events. This highlights why coordinate maps can be misleading when describing black hole horizons and distant space-time. So it means that physical things, like the things that are happening far away, have no physical significance to us. And while we don't see this in our day-to-day life, it's because that our speeds and our time are very close to each other. So like we are just on the same point. So it means that we are seeing the reality as now. But if we expand that, and if we go like millions and millions of light years away, we will see a difference. So like if someone is moving and if I'm sitting here and someone is moving, what would happen? Like if aliens invaded us, what would happen? If the fast moving person would perceive that the aliens would be still discussing on their planet how to invade this and that. So this is relativity or simultaneity. It says that now is subjective, and like we should not care about the things happening far away because they have no physical significance to us. So Saksham and Satyajit, did you get this topic? Yes. Saksham, did you get it? Okay. Yes. So let me explain it once again. So like let's say I'm sitting here and one person is moving. What would happen that if aliens started attacking us right now, that moving person would perceive that the aliens would be still discussing on their planet how to invade and their preparations. So this is called relativity of simultaneity. It says that now is subjective, and things that are happening far away from us have no significant physical significance to us. So it's just based on observers motion. So did you get it, Saksham? Okay, so this topic is essential for answering how black holes are forming and other things. So let's discuss about the future light cone. The future light cone defines the limit of your reachable space-time. Because light travels at 45 degrees, you cannot move outside this cone without exceeding light speed. In black hole physics, mapping this cone helps distinguish events that can escape the horizon from those that are trapped. So, uh, future light cone, it's a very important topic. It says the red part you see is then future light cone. It says that at the bottom part is the past light cone, and the above one is the future light cone. It says it defines our limits of that space and time that we are reaching. So we can travel anywhere in this future light cone, but we cannot exceed the speed of light, so we cannot move any further from that red lines, and we cannot enter the green lines. So so it's all about geometry, and about we cannot exceed the speed of light, so that's why we cannot escape our future light cone and move to the green part. So everything moves at the speed of light. In space-time, everything moves at a constant speed c. If you are stationary, your full velocity is spent moving through time. As you move faster than space, your motion through time slows down. Time dilation. Massless photons use all their speed in space, effectively experiencing no time. So let's take an example. If there's a spaceship going to a star and it moves, and it takes 3 years, and there's an observer moving, and it says that he witnessed that the spaceship took 3.5 years and it traveled only 1.8 light years to reach that. What would happen uh, that that time, that 3.5 light years is called the coordinate time, and that 3 years is called the proper time. So there are proper distances and many other things. These are all because everything moves at the speed of light. And we'll talk about this using the Minkowski space-time diagrams. So events that never happen. So events inside a black hole are physically real but exist outside our observable timeline. While an outside observer sees an object take infinite time to reach the event horizon, this is a limitation of the coordinate map, not a physical reality. Once inside, the geometry shifts, moving towards the central infinity becomes an inevitable time-like future. Additionally, an infalling observer does not see the entire future of the universe. They eventually lose contact with all external signals. So, okay, so events that never happen. So like in a black hole, that event has happened but it does not exist in our past, future or present. So how can I explain this? So let's take a table, and there's an ant on the other end, and there are coordinate systems. So after each step, the steps are halved. What would happen? That it would never even reach the ant. So it would never reach that ant, and it does not mean that the ant does not exist, but it does not exist in our reality, in our past, future and present. So did everyone get me? Are there any questions? Saksham and Satyajit? Yes. uh, can you repeat yourself? I didn't get it. Yes. Okay, okay, so this question can be restructured into what is the frame of reference for an photon. So this question was asked to Einstein, and he said that it does not exist. So I don't think so. I can't answer that. I don't, like he said that the photons do not have an frame of reference for themselves. Like it's we are asking the wrong question here. So uh, so that's the answer for it. So uh, do you want to say something else? No, it's okay. So as I mentioned the example that spaceship was traveling to a star. It took 3 years, and an other observer uh, noticed it, and he said that it took 3.5 years. But there are many equations for that. So there's the space-time interval. We use that to find the proper time it took for something to happen. So there are equations for that. I think so. It's d tau squared is equals to dt squared minus dx squared. So it says that if you move faster in space, you would be moving less in proper time. So uh, so did you get me these proper time and these the space time interval? Okay, so I I don't think so. I have an answer for that. So what do you think about that? Okay. I also had these questions. So Einstein said that the frame of reference of a photon does not exist, or something like that. I'll research about it more. So, so did you get this slide that events never happen inside the black hole? So, okay. So Saksham and Satyajit. So then, how does the black hole form? So, Saksham, I think so. Uh, do you have any guesses? Hello, Saksham. Uh, Saksham, do you have any guess for how that black hole forms? We have talked about the relativity of simultaneity and other things. Do you know how do they form? Okay, so how does that? So like Satyajit has raised his hand. So Satyajit, what do you want to say? Yes. Okay. Yes. So this is a yes. You continue. I was just saying that it's related to relativity of simultaneity. Okay. Yes. Yes. So, and that's the thing about relativity or simultaneity. It says that we should not care about things that happen far away because they have no physical significance to us. So, Saksham, did you get it? How did we answer that? How black holes are found? Okay. So, okay. So when an person falls into a black hole, should the person see the whole future of the universe in fast and forward? Saksham, do you know? Do you have any guess? When a person falls into a black hole, should it see the future of the universe in fast and forward? Okay, so like near the event horizon. Uh, so Satyajit has raised his hand. Hello, Satyajit. Okay. Okay, so you are right. And whenever he enters that event horizon, he cannot send any further signals because he's just cut off from the universe itself. And we also cannot enter that event horizon. Like we can enter it, but we cannot escape it because our future light cone gets cut off. So okay, so and if you want to save that falling person, there would be a threshold, and if we exceed that threshold, our future light cone, what would happen? That it would just that the person falling in would not be in the contact of our future light cone, so we wouldn't be able to save him. So this has things related to future light cones and these things. So Saksham, did you understand it? Hello, Saksham. Okay. Space-time interval. So this equation describes the space-time interval. It shows that our budget for motion is shared between time dt and space dx. If you move through space, your passage through time d tau must decrease to keep at the interval consistent. At light speed, space movements equal coordinate time, making proper time zero. In general relativity, it has metric tensors 2 for gravity or accelerations. So the equation goes like this, that d tau squared is equals to dt squared minus dx squared. So it says that if we are moving fast through space, a dx, what would happen, that the coordinate dt time, uh, which can also be referred as the coordinate time, would decrease to keep the interval consistent, and d tau is the proper time. So did everyone get this? Yes. Okay. So so uh, this equation is applicable in many places. If there's an observer and he observes that a spaceship has moved 1.8 light years in 3.5 years between two stars, and journey, and that but in the spaceship what people observe is that they have traveled 3 years. So what would happen that we can just use the space-time interval, that observer could use it, and he would find that this would be approximately equal to 3. And in general relativity it also has metric tensors for gravity or acceleration. Summary of special relativity. Special relativity deals with objects moving at constant high speeds. It introduces concepts like time dilation, length contraction, and mass energy equivalence. The theory relies on two fundamental postulates about the invariance of light, speed, and physical laws. And like in the space, if we make a diagram for that, what would we will see that the hypotenuse of that object moving would always be an invariant, but in space time what would we see is that its perpendicular would always be an invariant. Summary of general relativity. General relativity describes gravity as the curvature of space-time caused by mass and energy. It explains phenomena from planetary orbits to black holes. The theory has been validated through numerous experimental observations.